Hey there, how are y'all? So we're going to look at 5.4 and 5.5 on graphing square root and cube root functions. And so the objectives will be to graph and analyze square root and cube root functions with the associated standards here, ACE2 and FIF4, dealing with graphing functions. So a couple things we're going to talk about first is the parent function of square roots. And remember, when we talked back in chapter 2 about transformation of functions, we always go back to that parent function first. And so we want to understand what is the parent function of a square root function. And so remember that a square root is just like the square root of x, right? And so when we graph that, it gives us this picture here. And so look at the domain and range. We don't get a graph that goes on forever in both directions. It starts at the origin and is increasing as we go to the right. And so the domain is from 0 to infinity, and the range is also from 0 to infinity as this increases. It only has one intercept at the origin, so it has one x-intercept and one y-intercept, both of those being at the origin. There is not a point or line of symmetry with the square root function. It is undefined for any values of x that are less than 0. And why is that? Well, think about when you substitute into the square root. Can you take the square root of a negative number and get a real number? No. Now, go back to what we've talked about with imaginary numbers. Of course, we could get an imaginary number, but that does not plot on the real number coordinate plane that we have in front of us. The end behavior, so our end behavior is going towards the left. It goes towards 0. F of x goes towards 0, the y. And as x goes towards positive infinity, the y is also going towards positive infinity. It has one extrema, a minimum at the origin. Now, this is where, again, chapter 2 comes back into play very big, the transformations of square root functions. So the general form of a square root function is a times the square root of x minus h plus k. And so some of those letters look familiar, right? This a in front, remember that's the amplitude or our dilation. And remember, if we have a positive or negative in front, that could reflect it across the x-axis. And so go back to what we talked about in chapter 2, that a is our dilation. And remember, our dilation factor will be a vertical dilation, right? And remember, the sign would be the reflection across the x-axis. And so if I throw that negative out in front, instead of it opening and increasing, it's going to be opening and decreasing. Remember that the h is the horizontal translation. And remember that the x does what to you? What does your x do? It lies to you. And so if I see like x minus 2 in here, that minus 2 makes me think I'm shifting to the left, but I'm really shifting where? To the right. And then the plus k is our vertical dilation. Not vertical dilation, but our vertical translation. And so remember, that's going to shift this graph either up or down depending on the sign of that k. If the k is positive, it's going to shift it up, and if the k is negative, it's going to shift it down. So let's look at what this does with a couple of functions. So our first problem here is to graph y equals 3 times the square root of x minus 4 plus 2. And we want to state the domain and range of this function. And so the first thing we need to look at is the transformations that are happening, and there are 3. The first is this 3 out front, and that 3 would be a vertical dilation. The minus 4 in here, so that means it's going to be 4, and remember it's inside, so it's horizontal. And remember the x lies to you, so it says minus 4, so really it is a 4-unit shift to the right. And then finally a plus 2 out back, so the 2 is a 2-unit shift. In which direction? It's plus, so it'd be up. And so that's what's going to happen to our points. Now, let's go back to our parent function for just a second. I want you to look at a couple of points that happen. Obviously, we have the origin. We also have this point at 1, 1. We have this next point at 4, 2. And this third point, the fourth point at 9, 3. Because the square root of 9 is what? 3, right? So if we think about those ordered pairs, 0, 0, 1, 1, 4, 2, and 9, 3, and we're going to transform these points through these dilations. And so let's think about where these points will go. If I'm at 0, 0 originally, right, that's my parent function, a vertical dilation of 3 is not going to move me anywhere vertically because 3 times 0 is 0. But it will take me 4 units to the right. So 4 units to the right would end me up here, and then 2 units up would end me up here. So this first point, and I'm going to change the colors here, and this first point will be here. Now, my next point would have been at 1, 1, because the square root of 1 is 1. And so vertical dilation of 3 means 1 times 3 ends me up at 3. 4 units to the right, and 2 units up takes me there. And so again, changing my color, so my point is now here. So again, pay attention to the steps. Vertical dilation of 3, so my y value went from 1 times by 3 gives me 3. Shifted to the right 4 units, and up 2. My next point is at 4, 2. So it's actually where this red dot is currently. And so I'm going to multiply the y value by 3, so it takes me to 6. Shifting it to the right 4 units will take me out to the x value of 8. And up 2 more units will take me here. So changing my color again will take me to there. And so what I end up with, my parent function is this, minus the glitch. So again, we get this curve here coming out. That's the parent function. But the transform function ends up all the way up here. And so let's talk about the domain and the range of this new function. Well, where am I starting? I'm starting at the ordered pair 4, 2. And so my domain is going to be x is greater than or equal to 4, or I could write that as 4 to infinity. And then my range would be y is greater than or equal to 2, or from 2 to infinity. And so that's all we're doing here is looking at transforming these points. Now, are there other methods to do this? Sure, and I'm going to show you that on example B, what we can do with that. And so example B, we have the function y is equal to negative square root of x plus 5 minus 6. And so here's what I'm going to do in example B. I still want to find that first point because that's going to be very critical. But other numbers I'm going to put into this table are going to be values that make this square root nice for me to work with in the end. And so where's my starting point going to be? Well, remember this negative out front, there's no dilation anyways, and it won't affect 0 anyways. But this is going to shift me to the left of 5 and down 6. So where's my starting point? It's at negative 5, negative 6. Negative 5, negative 6 starts me here. And so if my x is negative 5 and I plug this in to this equation, and we'll see negative 5 plus 5 is 0. Obviously, the square root of 0 is 0. Negative of that's still 0. Minus the 6 gives me the negative 6. Now, what's the next nice square root number that I could get this from? Well, I could get 4 under here, right? And so what would give me a 4 under the radical? Well, if I subtract 1, so minus 1, negative 1. And so negative 1 plus 5 would give me 4. And that would give me the square root of that is 2. And then negative, so I'm at negative 2 minus 6 is negative 8. So I've got the order pair negative 1, negative 8. Now we can keep finding points that'll work here. If I do 4 plus 5, I get 9. So I could take 4, and so I get 4 plus 5 is 9. The square root of that is 3. The negative out in front makes it negative. Minus 6, so negative 3 minus 6 is negative 9. And so I end up at 4, negative 9. And so I end up, now there's one other point I could use. I could use negative 4, and we'll see just real quick what will happen there. This will be 1 inside, so negative 1 minus 6 is negative 7. Just again to get a little bit better picture of this curve. but that's our function there. And so again, we can use a table of values, understanding we want to use values that are going to give us nice square roots or cube roots when we get to those type problems that are going to come out not to decimal values and be ugly to work with later on down the line. So let's talk about the domain and the range of this problem. The domain is pretty straightforward here. Again, it's going to start where we started here, working to the right. So x is greater than or equal to -5. So -5 to infinity in interval notation. Now the range is a little bit different because I'm not increasing, I'm not going up in this case. So my y is not going to be greater than or equal to, it's going to be less than or equal to. And where does it start for the y? It's less than or equal to the -6. So it's going to be from -infinity to -6. Because remember, we always do interval notation from least to greatest. And so again, the -infinity would be our start, the -6 our end, from least to greatest. All right, so that's what we're looking at with those functions there. So let's look at a word problem here to deal with square roots. So when an object is spinning in a circular path of radius 2 meters with velocity v in meters per second, the centripetal acceleration a in meters per second squared is directed towards the center of the circle. The velocity v and the acceleration a of the object are related with the function v is equal to the square root of 2a. And graph this function with a domain where a is greater than or equal to 0. Again, it makes no sense to have a less than 0 for two reasons. One, because if I try to take the square root of a negative, it's not going to work for a real value. And number two, we're talking about acceleration, and the acceleration does need to be positive in these type problems. Okay, so, and again, that's just getting into the physics of it for those who have not taken physics. Okay, and so as we look at this problem, we want to, again, we could set up a table or we could set up our order pairs from our parent function and work from there. Remember that this 2 inside, we didn't talk about that with transformations in this section so far, but remember that the 2 inside is not a vertical dilation, but it's a horizontal dilation. And remember that, again, the x, or in this case the a, lies to you, and so it's not stretching it by a factor of 2 horizontally, but it's actually shrinking it by 1/2, because remember it's 1 over the b value. But here I'm going to take in some a values, and we're going to plug that into the square root of 2a and end up with our velocity values. And so if our a is 0, we do 2 times 0, and of course get 0. So I'm at the origin still. Obviously, again, if I'm doing a horizontal dilation by a half, multiplying 0 times anything is still going to give us 0. If I plug in 1, I get 2 under here, so that gives me not a great value. But if I plug in 2, I get 2 times 2. 2 times 2 is 4. The square root of that is 2. So I end up at 2, 2. The next value I can plug in and get a nice value out of is 8. We could do 4, but that gives us 8 as the square root, and square root of 8 is not nice. Our next number that's going to come out nice is 2 times 8, because 2 times 8 is 16. The square root of that is 4, and so I end up with the order pair 8, 4. And we end up with this picture here. And so when an object is spinning in a circular path, as the acceleration increases, what happens with the velocity? It also increases. But again, it doesn't increase as fast. So again, if my acceleration is at 8 meters per second squared, my velocity would only be 4 meters per second. Okay? And so what would the centripetal acceleration of an object spinning along the circular path with a velocity of 4 meters per second be? Well, that comes back up here. I need to find where my velocity is equal to 4. What was the acceleration? Well, that's coming here. The acceleration would be 8 meters per second squared. Acceleration would be 8 meters per second squared. Okay, and again, that's just going from our table that we found. If that value was not on our table, we could plug in this value for v, right, and solve for a, and those go through our steps of solving. So I would square both sides, and then divide both sides by 2. But again, we already had it in the table, so I didn't have to do any extra work for that one. All right, you have to scroll down units a little bit. I left a little bit larger space there because I deleted a problem from the old notes that I had for this. But let's talk about cube root functions. So like square root functions, the parent function of a cube root is a little bit different because can we take the cube root of a negative number? Yes. And so we end up with a graph that ends up going in both directions. And so my domain is all real numbers and my range is all real numbers. And for those of you wondering what this little E symbol is, this is just mathematical terminology for X is contained in, and then of course this R is the real numbers. Again, that's just notation that you'll see from time to time, and I just want to introduce it here just so you can see it. It has one intercept for X and Y, and that is at the origin for the parent function. It does have point symmetry. Now, go back to chapter 2 when we talked about point and line symmetry. Remember, point symmetry is where I can rotate the graph 180 degrees. And so I could take a point over here, like the point over here at 8, 2, and it rotates around 180 degrees to the point, at -8, -2, right? Because again, it's going to flip both the X and Y values from positive to negative or vice versa. There's no line symmetry on this. In behaviors, as X goes to positive infinity, the Y is going to positive infinity. As the X goes to negative infinity, the Y goes to negative infinity. And we have this last piece of information here called an inflection point. This inflection point, what it basically means is this curve in the graph, right? So we see, like normally we think like maybe an exponential function, it would just keep curving upward forever, right? But we change what we call concavity. And again, we're going to get into this more in pre-calculus and calculus if you choose to go so far. But again, just kind of introducing this here today. But you'll see the graph changes from being what we call concave up because it's able to hold water here to concave down where the water would spill off the top if we were pouring water from above. And again, like not super important here, but it will allow us some help in graphing these functions. And so when we think about cube roots, some ordered pairs that come in to help us, obviously 0, 0. When we take the cube root of -1, we get -1. And when we take the cube root of -8, we get -2. And we'll also get the positives of those, 1, 1, and 8, 2 on our graph. And so when we deal with transformations, we deal with the same transformations that we dealt with square roots, right? So again, the A out front being our dilation and reflection, the X minus H inside, so that -H being the horizontal translation, and the plus K out back being the vertical translation. And so let's look at what this does for a couple of problems below. So let's look at this graph here and talk about the transformations that are given to us. So there's no dilation factor here, but we do have a horizontal translation and a vertical translation. So the 4 will be a shift 4 units, shifted where? Is it going to be left or is it right? It's a +4, so remember you're thinking it's going to be right, but it's really where? Left, because remember the X does what? Lies to you. The 2 is going to be where? 2 units shifted where? Up. And so we're going to take these 5 ordered pairs that we had here from our parent function, and we're going to shift them these coordinates. So I'm going to start with 0, 0. And so I'm going 4 units left and 2 units up. So 4 left, 2 up ends me up here. And again, I'm going to change from orange to red with the transformations. So I have the order pair 1, 1. And so 1, 1 is going to go 4 to the left and 2 up and end me up here. And so now that's this point. My next point is 8, 2. And so that point, 4 to the left and 2 up ends me up there. And so I'm going to turn that to red. And then if I come back this way, I'm at -1, -1. And so 4 to the left and 2 up will take me here. So that's here. And my last one will actually end up not on the picture, but at -8, -2, 4 to the left would end me up out here, and then up 2 would end me up with my x-intercept at -12. So again, I would have a red dot out here. And so my original function is going to be the orange, and so it comes in like this. Again, you've got a concavity change. Again, it's not a perfect straight line in the middle here. It'll look like that. And our red, again, coming in like this, curving up and through. And again, it should go through that point there. All right, so that's where we're at. Again, we could do a table like we did with the square root functions, and we'll, just for the sake of time, I'm going to just briefly talk about that table with this one here as we plot it up. So again, I would look for that inflection point first with the cube roots. And so where's my transformations going to be? Well, this gives me the order pair 1, 3. So 1, 3 is here. So if my x is 1, my y is 3. Because if I do negative 2, cube root of x minus 1 plus the 3. So negative 2, cube root of 1 minus 1. I'll put that cube root there. So that's 0. 0 times negative 2 is still 0, plus the 3 gives me 3. So again, I'm looking for values that are going to be nice to take the cube root of. So again, we want to get numbers of like 0, 1, and 8. So what's going to give me 1 under here? So that'd be 2 minus 1. So I'm going to get 2. Cube root of 2 minus 1 plus 3, so that's 1. Cube root of that's still 1, gives me negative 2. Negative 2 plus 3 is 1, so I'm at 2, 1. My next value, again, I want 0, I want 1, I want 8, both positive and negative with cube roots. And so to get 8, I would do 9 minus 1, and so I'm going to do 9, negative 2 times the cube root of 9 minus 1 plus the 3. That gives me 8. Cube root of that is 2. Negative 2 times 2 is 4. Negative 4, excuse me. And then negative 4 plus 3 is negative 1. So I'm at 9 and negative 1. Now, I want to get points in the other direction as well. So I want to get negative 1 underneath here. So what would give me negative 1 when x is 0? And so I'm going to get the cube root of 0 minus 1 plus the 3. So this is negative 1, still negative 1 when I take the cube root of it. Negative 1 times negative 2 is positive 2. 2 plus 3 is 5. So I have a y-intercept of 5. And then I want to get to negative 8, so that's going to be at negative 7. And so negative 2 times the cube root of negative 7 minus 1 plus the 3. Negative 8, cube root of that is negative 2. Negative 2 times negative 2 is positive 4. 4 plus 3 is 7. So I'm going to get negative 7, positive 7, and so my graph will look like this. Again, my x-intercept is a little hard to tell. It's going to be somewhere between 3 and 4. And it might fall just before 3, but again, it's not perfect, but my expectation would be somewhere between 3 and 4. So that's our function there. And so attributes of the graph, where is our inflection point? That's one of our big attributes here. So the inflection point, where's it at? It's right here. It's where we found here. It's at 1, 3. Domain and range. What's our domain and range? Well, for both, it's all real numbers, right? Negative infinity to positive infinity. What else is important to this graph? End behaviors, right? So the end behavior, as x goes to positive infinity, where's our f of x going? Or where's our y going? Our f of x is going to negative infinity. And as x goes to negative infinity, where's the f of x going? It's going to positive infinity. So again, that's what we're looking at with these graphs when we talk about critical behaviors. Inflection points, domain and range, end behaviors, max and mins. Again, cube roots won't have maxes and mins, square roots would. But that's what we're looking at there. All right, and so this last problem here, again, is kind of like our square root problem, and I know I'm running a little long on this video, combining two lessons together, but the weight range for American bison is between 422 and 998 kilograms. The height of some bison weighing X kilograms is modeled by this function here. And so graph the function for the domain from 0 to 1,000 kilograms. And so again, we could use a table to get this. Again, this is one where I would use technology to get these values very quickly. Obviously, we're going to start at 0, 0, plugging in 1,000. Cube root of 1,000 is 10. 10 times 0.2 would give me 2. And so 1, 2, and if I'm all the way out at 1,000 kilograms, right, and I'm at 2 meters, because we're dealing with this in metric, so my bison would be 2 meters tall and 1,000 kilograms. Other value I could plug in here that would be really quick and easy to figure out. I could plug in any cube root that would be nice. So cube root of, for example, 27, cube root of 5. To get 5, you would have 125. 6 would be 216. 7 would be 343. So, we can get some particular values as we go along this graph to get certain values. But they give us 2 values here, that the weight range of bison, right? And so that's what we're really looking at, and that's where these graphs, these problems will continue through. And obviously domain stopped at 1,000, so it would not continue past that point. So analyzing the graph, obviously the taller the buffalo, the water buffalo, it was water buffaloes, right? Yes. No, bison. The taller the bison, the heavier it is, according to this model. Key features of, again, looking at that this is an increasing function. We wouldn't talk necessarily about maxes and mins, but we would start at 0, 0, go to 1,000, 2. And what is the approximate height of a bison at 500 kilograms? That's just plugging into the function. So if I do, let's get our function back from up here, h of x. So h of 500 is equal to 0.2 times the cube root of 500. You would need to find the cube root of 500. So the cube root of 500 is about 7.937. We'll multiply that by the 0.2. And so if I have a 500 kilogram bison, we'll get about 1.587 meters is that buffalo's height. And again, that's just dealing with the function. You could do that on a graph as well, using Desmos or using your graphing calculator to get that value. All right, so again, I know this video has been long, but again, combining 2 sections into one here because they really go hand in hand. And so today's word of the day is radical. Again, radical, R-A-D-I-C-A-L. And so make sure you get that into the Google form. Again, I hope y'all have a great day. And if you need any help, get on that Google Meet, send me an email, and y'all have a great day.